Welcome everyone, welcome. We are going to wait just a few moments here to let attendees into the webinar. But we will get started here very shortly. Okay, it looks like we're starting to kind of level off in terms of the attendees, so we'll go ahead and start the broadcast here. Welcome everyone to the second session of our Whole Tomato, or I'm sorry, this is not the second session, this is the fourth session of our Whole Tomato Summer CodeFest C++ Coding Camp. And my name is Ben, I'm Chief of Staff for Whole Tomato, who is sponsoring this webinar. So far, we've had a lot of fun covering some interesting topics in this series. I've heard from some talented presenters, and we have another one for you today who I'll introduce shortly. Before we begin, I do want to let you know that we'll have Q&A at the end of the presentation, so please type in your questions in the questions panel as you have them. So far this series, we've really been able to get to nearly every question that's been asked, and we've received some really great questions, so really encourage you to submit those questions throughout the presentation. We have one more webinar after today's, so make sure that's on your calendar. And we are recording these and posting them to our YouTube channel. So make sure you're subscribed to that so you can receive notifications when these webinars are posted. You can find our YouTube channel at youtube.com/whole-tomato-software, or you can just search YouTube for Whole Tomato and we'll come right up. So speaking of, again, this webinar is sponsored by Whole Tomato. We publish the highly popular Visual Assist extension for C++ and C# development in Visual Studio. And if you're not yet a Visual Assist user, but you are a C++ developer who works in Visual Studio, we invite you to check it out. We have a free trial available. You can get it on the Visual Studio Marketplace or download it directly from our site at wholetomato.com. Visual Assist is a powerful coding assistance and refactoring tool that does things like code inspections and legacy code refactoring. It also has some really helpful navigation tools. In general, just really makes the life of any C++ developer much, much easier. Also, Visual Assist is written by developers for developers, so it doesn't get in your way or bog your IDE down. So check it out if you haven't already. All right, back to today's topic. I'm pleased to introduce today's presenter, Miguel Moreno. Miguel will be speaking on tips and tricks using C++ templates. He's a C++ veteran with over 3 decades of experience. And as seems to be a common thread with some of our other presenters, he got his start with BASIC on a Commodore 64 and on one of the old Casio portable computers. He went into electrical engineering, and that introduced him into assembler, Fortran, Pascal, and eventually C and C++. Currently, Miguel enjoys working on embedded device programming and IoT programming, and specifically focuses on low latency, high performance applications like industrial automation, gaming, fintech, ML, and AI. A lot of really great, interesting stuff that Miguel works on. He resides in both San Diego and Hong Kong. He's currently in Hong Kong, and he switches between the two depending on what project he's working on. And outside of programming, he likes to be outside, hiking, and doing other outdoor activities. So he has a lot of good content for you today covering C++ templates, and I'm sure he's eager to get started. So with that, Miguel, I'll hand it over to you.
Thanks, Ben. Hello, everyone. My name is Miguel Moreno. You just heard the introduction by Ben. What we'll be presenting today is some tips and tricks about how to use templates. Maybe for some of you, like what's happening with templates, but let me just share with you some of use cases that I have found myself, both with my own projects and the ones I've seen with either customers or with other colleagues and fellow developers. So I wanted just to share these quick tricks. So number one is templates. Most of us think that the templates are a very complex thing to grasp and handle. Just take a look at any of the standard library templates or the Boost library, and you would see that the source code looks like out of this world. And that's because they are fairly complex. They are doing a lot of type inference and then some traits for detecting the type. So no wonder those are really the advanced way to use templates. And that's why many people find, oh, it's not my cup of tea. I'll just use those that come embedded in, already included in the standard library, or I will use those from the Boost library and just stay with that and I won't do anything else. So what I'm trying to cover is some normal use cases that you see with a normal, with our normal day-to-day projects and applications that for some reason are very good candidates for using templates. What I'm showing right now on your screen, sorry about the handouts, the presentation. I may send those later, but I'd rather focus on the sample that I'm showing to you. So I spent some time making sure that it works, which I think was the key for presenting you rather than presenting the slides. But I'll have some slides for you, but just doing it live, I think will be more appropriate for you. This is one use case that is very recently being used. Linear regression is one of many machine learning models used today. To some of you, this might come like a what's that? Well, actually, linear regression, it's a very old model. You may find the whole explanation here in Wikipedia. But the whole thing is what you can see here is that when you have some data collected randomly out on the field, then statistically those dots will follow some pattern. And usually, what you want to do is try to come up with a formula that represents these points accurately as much as possible. So then you can do some forecasting, or in scientific terms, you are modeling the behavior of these data points. So as you can see, statistically speaking, the more dots you collect, in other words, the more data that you collect out from the field, from measurements, the better, because then you get a better, you can do a better model that represents more faithfully what is out there. I chose this one not because of the templates, but because of the use case, which I see very common with complex applications that try to use advanced algorithms. So this one is fairly good algorithm, linear regression, without going too complex and lose the focus. So to me, it's a pretty good example to show you how to embrace templates in your C++ application. Okay, having said that, again, if you want to go into the details, but again, this is a lot of a statistical thing. One thing you need to be aware of in case you're interested in doing some linear regression on your own or getting started with machine learning algorithms is in this very specific case, linear regression, as the name implies, is those dots that the behavior follows some kind of a linear line. So they follow a line, as you can see on these ones. These dots on the left upper hand would be good candidates to be applied to a linear regression, because even though they are scattered, on the average, they follow the line. The one on the top right hand is not a good candidate for linear regression. You can see that it has some curved behavior. There are other models that you can use to represent this set of dots. The one on the lower hand, left hand lower part is also a good candidate. And this is something that normally happens with statistics points. You can see an outlier, a dot, very far away. Normally, there's some formulas to discard those, either discard them or include them in your analysis. But normally, this is okay. You will always have some outliers. And the one on the right-hand lower part, you would see that's definitely a no-go. You can see that it's basically following a vertical line. So that one would be a big mistake if you try to model it with a linear regression. Okay, the reason I mentioned this is because there's many more applications nowadays to start using these machine learning algorithms. Here I have a simple example of some collection of dots without going too crazy, just enough to make the explanation quick and graspable by all of you. You can see here that we have a collection of 6 data points with some collected values out of the field. Those are represented by the blue dots over here. And what we want to come up with in this case is introduce one of the many methods, algorithms, to come up with a linear regression model. That would be how to come up with a formula that represents that green line that you see on the screen. So that green line is actually the modeling that represents these data points. So I'll switch now to some basic code. So let's say we need to try and come up quickly with the algorithm that creates this linear regression model. And what we do is many times you just go with a quick and dirty console application that just works, that you can prove the concept that the algorithm that you are trying to model is okay. This is the application I'm showing to you right now in C++. This is a very basic application, console application. We define a basic class. We define some private members, vectors to hold both the X values of the random data values, the sample values, and also the Y values. So we have 2 vectors that hold those values here. Then we have other parameters. And just bear with me, this class has a constructor and has enough methods to do the whole thing, do the whole iteration. Now, if you have ever seen this kind of numeric solution algorithms, the point is that these are the kind of algorithms that don't have an exact answer. You cannot just type a formula and immediately get a result from a calculator or Excel. These are the kind of algorithms that you need to do iterations and then define some sort of error limit or error gap, which normally in scientific terms, you will see it called epsilon. They will call it also drift with another term. So this is one of those algorithms. Linear regression, even though it's one of the simplest ones in machine learning, still is one that needs iteration. It's not a finite answer. You need a sort of iteration until you get a fairly good approximation. Now, because of that, one of the parameters for the algorithm is how exact you want it to be, how exact the error, what is the minimum gap of the error that you are willing to accept before the solution is found by the algorithm. So you can see some of those parameters are over here. And again, this is a fairly good simple implementation of linear regression. I'll just run this program so you can see how it works. I'll do it here. Then I go to the command line. Well, let me compile it first. Compile. Okay. Go to the command line. Then we'll run it from here. Depending on your refresh screen, you can see the iterations running as the algorithm tries to find the solution, to find exact parameters that will represent the linear regression for those data points that I've showed to you. You see that the program starts by showing the initial values that I'm feeding to the algorithm. So I'm feeding the initial values A and B on the step, which is one of the internal parameters of the approximation of the solution. And finally, you can see after 1,120 iterations, it finally found the solution. What this means here is that it had found the right values are the ones that you see on the screen. So the one here, A, is one of the parameters, and the other one is B. In a linear regression, that means is the parameters that define the line that will represent those dots. And these are internal values used by the algorithm. and this is the final error. This error actually is standard deviation accumulated over all the data over the parameters found for this line. So it's not perfect. This is kind of the deviation that you achieve by trying to model those dots. If we go back to the screen that I showed to you at the beginning, you can see that those dots are not a perfect line. So those dots have some variation over that green line. So that variation, the bigger it is, the farther away they are from the line, you will get more standard deviation from the algorithm. Sorry about that. So this error internally is actually part of the standard deviation. Okay, but the point here, what I want to show you is we have achieved our goal. We can tell our boss or our customer, okay, I got it working. I have a machine learning algorithm that is working. It takes some fair amount of time. We can do some timings. We can get some results. Here at the end, I'm just a sample after finding the right values. I'm applying it to two values. Once we have the line, that means that we can project any value. We can assume that given any input value, I can deduct or prevent what is happening on, hold on, let me switch the screen again. Sorry about that. So yeah, at the end, I'm showing these values, which are sample values calculated from this. So this value 3.8 and 7.2 on the X don't exist in the original data points that I'm using for the algorithm. These are being fed to the formula, and then I get the projected X value. Now, linear regression can, in this case, I'm using a single variable. I'm using an X as the independent variable to deduct a Y. But there are versions of linear regression that you can have multiple independent variables. And it's fairly used today for those machine learning algorithms that you can model with a linear approximation. So it can get fairly complex, and then the calculation time is order 1 or 2, depending on how many variables. It can get to logarithmic order. So some of these algorithms, once you have at least 5 or 6 independent variables being fed to it, can take up some hours to run. So don't be fooled that what you saw over here on my screen ran pretty quickly. That was intentional, so I can just explain to you the concept. The point here is you have a really heavy algorithm running. And usually in these kinds of applications, people want to know what's going on. What's the progress? How good are you doing in your progress? And by when will it be done? So just implementing the algorithm, as I just did on this application, is one step. But giving feedback is a very key thing for this kind of applications. And I've noticed that there's a lot of projects out there with very complex algorithms that take some fair amount of time to run, and there's barely any feedback for the end user. So they get desperate. Or if it's running a batch job, to get some idea of or indicator of how good they're doing or what is the percentage of advance. So some developers still nowadays somehow forget to give this kind of feedback to the end users, which to me is always critical. That's part of the user experience. The user experience is to let the user know what's going on as much as possible all the time. Okay, so the code that I showed you here is, I added those, you can see them here, all these standard output lines, to give enough feedback from the internal parts of the algorithm. But what happens? We show this to our boss or the customer, and then he says, okay, good, fine. Can you put it in my iPhone? Or can I have it on a web page? Or can I have a nice GUI where I can chart those numbers and export them to Excel? Then that's when you start to struggle, because it took you some fair amount of time to put together this complex algorithm, which again is not a simple algorithm of 2 lines. It's an algorithm that in the example I'm giving to you, it may be 100 or 200 lines, but that was intentionally for showcasing this to you. But some of these algorithms are really, really reaching more than 1,003 more lines of code just to put together the algorithm. So how do you refactor this in order to quickly move the algorithm that you have just made to work, to move it quickly and faster into any other kind of application quickly? Now, I did this intentionally because just moving a console application to GUI is already a big task. Now, moving it to web and then moving it to iPhone or Android is, each one of them introduces a big burden and a big effort. It's not just redoing the algorithm. Now, if you encapsulate the algorithm in a class, like the one that I showed to you here, this class, hold on. Let's say the class that we have here, the linear regression class. And I remove everything that makes the feedback and the output on the screen. I remove that. Then I make it just a single functor linear regression class that I can use. Then I can use it everywhere. But then I'm losing the feedback features that I already added here. And then the other option is that then you do copy paste of your full class, linear regression class, and then you have a custom version for your console output. You have a custom version for your Windows GUI. You have a custom version for your iPhone, one custom version for the web app. So finally, you end up doing copy paste and replicating the same class, where you will only change those parts that give the user feedback, because this user feedback is embedded inside the core steps of the algorithm. And this is the use case that I want to give you an idea of how you can make your life easier. And how to do it? Well, by using templates. And you don't need to be a guru like those from the Boost library or the standard library. We're using templates in its most basic form, but very effectively. So the first thing we need to do is just refactor this class and make it aware. Number one, extract all these portions that are making the feedback, the user feedback. So you make a generic function. Now, I've done this in this next application. Next one, let me show you over here. So this second application, it's still a console app in C++, but the difference is I've done that refactoring with the classes. So I'll show you how it works. This is the file defining the class. Now I made it a template. Why? Because I'm templating the type of application that will be bound to. So basically what I'm doing is make the linear regression class aware of the application that it will be bound to, so that it can do some sort of calling back to the app and tell it where to do the feedback. I know some of you are already saying, oh, that's already done many other ways. Bear with me for a second. I'll just let you show what's the idea behind this. So the rest of the class is the same, but what I've done is you will see that all those areas where we had some feedback to the user directly with console output, those have been replaced with functions like this one. Let me just change the font size a bit so you can be aware of what I'm showing to you. So it'll make your life easier to read it. Okay, good. All right. So this kind of lines, I introduce a new member to the class, which is called Emp-app. And the class of the Emp-app is defined by the template. The class type sent on the template will define the type of the app. Therefore, when we are calling here Emp-app, it will call this function, which I call user interface algorithm start. And then I'm passing over the parameters it needs to show on the screen that the algorithm is starting right now. Okay, so that's for the start step. Now, while you're doing the iteration internally, I have replaced all the output to the console with this other function where we are calling the app member with this function called user interface algorithm progress. And then the parameters are those enough parameters needed to show on the screen the progress for this iteration of the algorithm. and so on. So every single area where I was directly doing a console output, I replace it with a function, a genetic function based on the parent app that is using this library. This is where you are defining the error, whether the error is good enough or not to end the algorithm. This function is called user interface converged progress. In machine learning, when you call it converged, this means when you have reached the minimum epsilon or the minimum gap that you are allowing for the algorithm to say, okay, enough. You have approximated good enough to the final result. So this is the name for showing the converged progress here. So now that I've done that on the basic linear regression, number one, the linear regression is now user interface agnostic. It doesn't know anything about the user interface. It's not using IO stream, it's not using standard output, none of them. So I even remove them from the includes here because it doesn't need them anymore. But there's the next step is once you have done that, is what we need to do is define a class that implements those routines that have been highlighted over here. Then again, using this very same console application, we go here to the console app. And what I've done is I'll do a quick comparison so you can see where we came from. We came from having a single monolithic application where the class had everything. So this linear regression class had all the user interface scattered and embedded within its internal routines and methods. So our main code was here. Let me show that to you here. So the main code was doing standard, I'm starting the application, and I'm defining the X and Y vectors for the data points that I need for the linear regression, creating the linear regression class, and then start the algorithm by giving it the maximum number of iterations and the starting points for the A and B parameters. Finally, when it's done, when it finishes, then I create two test values and then show them on the screen. So everything was in one single monolithic application. Now what I've done is we have created a new class called Linear Regression Console App. This is a new class. And this one has the only purpose of implementing those user interface functions, the ones that we are now calling from the linear regression app. So you can see here my comments. The first one is showing that the application is starting. The next one is called at the algorithm start when it starts calculating the iterations of the algorithm and also show some header here. Then this is the one shown for each step of the algorithm, for each approximation. This is the one when you need to show some convergence progress. This is the one for the regression parameters when it's done, when it's finished, then to show on the screen the final parameters. And then the one when you need to show some samples, some sample values calculated with the final model that you have created. And as a utility function, a run function that drives everything. Since I'm creating an app class, well, let's put everything inside the class. So it looks tidy and nice, and we're following our object orientation with this application. So the run method is here. It's not strictly needed, but it's just to comply ourselves to having a tidy and nice application class. So the run method of this app is doing what was done on the main app before. So this portion that was done on the main app, sorry about that here. All this portion is now done on the run method of our new application class. So it's setting up the vectors with the X and Y values, then creating the linear regression. You can see here that now I'm using the template. Number one, there's a new parameter. Before, I'll do a quick comparison here so you can see the differences. In the original code, we only needed to call the linear regression with the X vector and the Y vector, and then the epsilon, which is the smallest gap to approximate to the final value. That was only the original code. But now with this newly created regression class that has a template, then the first thing I need to do is on the template, tell it what is my app type, what is the class of my application. And then the very first parameter, which also you can see on the constructor of the class, the very first parameter in the constructor is exactly that one, the application. So we just made it the very first parameter for the class. So now we're using a template, our own template. We're telling it the type of the class that we just created, and then we're passing a reference to that app here. And then the rest is the same thing that we had before, the X and Y vectors and the epsilon value. Then we run the algorithm. And then at the end, we show the parameters once the algorithm has finished. And then we create two test values. And then we call the functions to show those test values on the screen. Let me run this application so you can see how it works now. I'll compile. Okay, let's go here. You may or may not see the iterations depending on the refresh over the internet on your screens, but right now it's iterating 400, 500, 600, 800. So this one achieved the final result with the epsilon that we set as the minimum gap of the approximation in 800 iterations. Now you see here the output. This is the model. So this is the linear regression. This is the formula that represents the line that models the data that we have input here. This is the model. And these are the values A and B that come from the cycle that created it. And then we have two sample values again calculated based on that model. So for an X value of 3.8 and 7.2, we get these values of Y equals 7.0 blah blah and Y equals 12.4 blah blah blah. You see that it runs exactly the same. So from the end user point of view, from the end user perspective, they see no difference at all. But here is why we did this. It starts to pay off almost immediately, just because after we have done that due diligence of creating our separation into core linear regression class by incorporating those methods and creating our new application class, the first thing you will say, well, I didn't really save much time. I had to create this new class here for the console app. That's true. But guess what? Once you need to move to a web-based or to a GUI-based application, you will always have a class representing the app already, depending whether you're using MFC with Visual Studio on Windows, or the VCL if you're using Embarcadero C++ Builder, or FMX FireMonkey if you are using the multi-platform version of C++ Builder with FireMonkey. So no matter what, once you moved to GUI or web-based, most likely you have an application class already. And by using the templates, you do something that many people envy from Python. In Python, you have duct typing. So duct typing means that Python doesn't care if the function was inherited from a master-based standard class or not. Python at runtime will do a check whether the signature of the function that you are calling, like this one here, at runtime, it will only check that the function that you are calling matches the same signature, that it has the same parameters it won't even check if the parameters have the same type. It will only check that the number of parameters are the same. Well, even simpler than that. So, but we are emulating that very effective and nice, neat feature of Python by doing these templates. So again, the only additional effort that we may be finding is if you start with a console class, because the console applications usually you don't have any base application class to start with. So in this case, yes, there was an additional burden to do it. But you know that console applications many times are very forgiving. So they are many times the easiest way to start, especially when you are developing these highly complex algorithms where many things can go wrong and you need to debug a lot of lines. So going with a console application as a first step is very helpful when deploying very highly complex and advanced algorithms. Okay, so once I've done this, I can then go and start a GUI application. Here you see the form design. This is a VCL application. This is a GUI framework by C++ Builder by Embarcadero. So this one, when you create the form, the framework itself will create a class. This is the class created by the framework. Is the read from form. It has a base class that defines the GUI forms, the graphical user interface forms. So from that one, the custom design that you have here on the screen, this framework creates a deriv class, which is your own, and you name it. In this case, I have named this deriv class linear regression app form. And this one has, you see here, all these members represent all the visual components shown on the screen. This is already done by the visual editor. So this is one of the great things when you start using frameworks, is that they ease the life for you. They ease our lives for making the frameworks. And as I said, you already have this class created because of the framework itself. Then the only thing I need to do is add these functions. Add the functions from the template that I created. So the same template that we have over here for the linear regression. So I just need to implement those functions that it is expecting to do. So no need to inherit or do something crazy or fancy. Simply add them up to the class that was already created by the framework. And once I do that, then I need to define the code. So here you can see the implementation. Of course, this is totally different from the console app. Now you're actually doing specific GUI logic, calling the visual components and updating them on the screen, blah, blah, blah. But this is done in these small functions, which is something that you would have to do anyhow. But here, I'm not even touching the algorithm class. So without even touching the algorithm class, I have made a GUI application that will work exactly the same as my console app without having to tamper with the algorithm. I don't need to touch it. I don't need to run the risk that I destroy something or I make something that was working on the console app, suddenly it won't work. I only need to implement these functions correctly here on the GUI domain, but the core logic of the algorithm is untouched. So this file that I showed to you is exactly the same one. It's the same definition, the same file, linear regression.h. It's a template, so it's on the header file. This is exactly the same one used on the console app. Is exactly the same one that now I'll be using my GUI app. So I'm only implementing these functions on the GUI side. And then again, I have also a run method. And guess what? The run method will be called when I push the button. So since a GUI app, I hook up the event of the button here, and then I'm calling run. Let's run this application so you can see how it works. Oh, sorry, I need to switch. Sorry about that, I need to switch the application. So let's switch it to the application number 3, which is the GUI one, the GUI based. Okay, I'm set now. All right, so here you can see my GUI application. Since I'm with a GUI application, then I can even take the luxury of changing the parameters myself before starting, or even adjusting the step here. Then I click start. The actual runtime is a bit slower, of course, because we are on a GUI application. But you can do some tricks on the actual update of your. You can see now that when it finished, it updated here. I have the final model. So you have this nice visual representation of the linear regression model that represents the original data points. You have the parameter, which you can copy paste parameters A and B, which again are the ones on this modeling here, and then two samples here representing them. So I can do copy paste and use them for modeling as I show in the other spreadsheet, and then do the modeling with these numbers. I will show you, if you want to speed it up, you're already in the GUI wall, so you may not necessarily want to update on every single item. So that's easy to do. So I will just go to the algorithm progress and just check. Let's say I want to do it only every 10 iterations. So I'm just checking. I'm sorry, I need to put it backwards. I will go through the update here only every 10 iterations. On the rest, I'll just return quickly, so I don't affect the runtime procedure. Okay, I click start. Oh, I didn't do the other one. Let me just finish it. I have two windows here. One is for the iteration itself, and the other window is for the error. So they need to be in sync with this. We could have some common parameter inside if we want. But then again, that's left to you. I just want to show you the concept of how you can do that and avoid this from making a big impact on the actual runtime of your complex algorithm. Here, good point. Okay, what I will do here. Well, I will leave it for later, and we just need to introduce an internal variable, so like a flag, because when you're calling the converge progress, I didn't set it to pass the parameter of the iteration, which would be fairly easy to do, by the way. Actually, we can do that. Let's do it. We just need to change the base template class. So now we're changing the class to allow it that when it calls converged, we also call it with the iteration, but the iteration is not here. Yeah, the iteration is separate. It's part of another process. So anyhow, I just wanted to show you what happens here. But the point is, we can set a flag, but it will take more time than I have now for you. So I'll leave it as a homework. Let's go back to the original one. Yeah, actually, let me just do it. I think we can do that fairly quick. I'll just put a flag. Since the iterations is always run first, then I can do this on the form side only. I don't need to go to the template class. I'll just do a private flag. And I go here. You may say, maybe wondering why I'm using this naming convention. I know this is not the standard C++ convention, but on VCL by Embarcadero, this is the naming convention on the field name. So I'm just following the coding standard for this one framework. So I'm compliant, and any other developer that wants to read it will know what I'm doing. So here F stands for the field of the class. And then I need to do it backwards. If it's a multiple of 10, then yes, we need to show the progress. If not show progress, then return. And now I can do copy paste of this one here. Because this field, this member, is being shared at the application level. So the linear regression has nothing to do with this. This is an internal member of the app. I added it to the class of the application, the GUI app. Then this is the way this one communicates with this one. So this routine algorithm progress is communicating with the converged progress through an internal private member of the application. This is totally on the GUI side, has nothing to do with the actual linear regression class. Okay, then you see now they're in sync. And it's running a bit faster. Still, you have the overhead of the visual thing, but overall, I would say right now the impact is about 20%. And this is, again, some of the things that I found with these very complex algorithms is the value of adding feedback to the end users of what's going on totally overweights whatever loss in performance you may have, as long as you do your due diligence, like in this case, having it update only every 10 iterations instead of every single one, you're achieving close to the final speed, like around 80% of the speed. That's understandable, and the end user will not complain. If you make it like I originally had it, like every single line, and you make it double, triple the times, yes, they will complain. But this is part of our normal due diligence every time you need to do some clever updates on the screen. And the same way, I just wanted to show you this because the same way I could quickly make this GUI app, the same way I could move it to another kind of application, a web application, or going to an Android app, or going to an iPhone app. The only thing I need to do is hook up to the class defining the app, like in this case, linear regression app form, hook up and add my own methods. And this is the whole point. Let's go back to what when I was saying you. What I wanted to show to you is, in this case, it looks very stupid or even like naive, but this is a very powerful use of the templates. And what we are doing, again, is some sort of a Duct typing. C++ will not allow you to pass the methods just freely here like Python does. But once I use a template, then of course C++ will do a type checking at compile time, and it will make sure that you did your due diligence and actually implemented all these methods over here. But other than that, we're making Duct typing, meaning you're only matching the signature of the classes, the methods, the functions, matching them regardless of the base class that holds the application. And this makes it very powerful. Now, going back to what many of you might be thinking about this, well, we've done this a lot of times with callback procedures. Well, think about implementing all these functions with so many different parameters with a callback procedure. Yes, I've done that in the past, but then finally you end up with a callback procedure when you need to pass all the possible parameters all the time. And sometimes you need to send some dummy values because on the step you are at, you actually don't have access to that specific value. So number one, you need to make, the problem with callback procedures is one single signature. So you need to have one single big signature with all the possible parameters. And then you need to, one of those parameters has to be some sort of flag to tell your application where I am at. Then finally, you introduce either a flag or some enumeration or whatever to tell them, oh, I'm now in the iteration steps. Oh, now I'm at the end. I already had the calculation. So it ends up very cumbersome to implement. Yes, this has been the traditional old style. But by using the templates, you don't need any of that. And your code is very, very readable, very easy to understand. And again, that's the whole idea of object orientation, but combined with generic programming. So because of the templates, I'm basically doing duct typing in C++. So this is the end of my presentation. So let me show you again the original regression model.
Awesome, Miguel. Thank you so much for that very informative demo and presentation. We have a couple minutes for some questions, and I think you just kind of spoke to this, but we do have quite a few questions asking about the pros and cons of using templates over classes. And then maybe you can speak more to when do you determine whether to use templates versus polymorphism, and are there any performance considerations between the two?
Thanks for the question. This goes back to 101 theory about C++ on templates. This is a quick answer. Polymorphism works great, like for creating the visual components on this framework. Almost any graphic framework out there, VCL in the case the one I'm showing to all of you over here, or FMX or MFC with Windows or blah, 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 use polymorphism because those classes they fit exactly to what you would use on polymorphism. Most of the behaviors, the methods, and the behavioral functionality is inherited. So you are just adding this small difference of, let's say, from an edit field over a list box, over a button. So those tie neatly. But in this case, what I'm showing is exactly the opposite case. I'm not doing any polymorphism here at all. What I'm doing here is how can I make my base class, in this case, the linear regression class, be aware of the application without having to know the application. In this case, I don't need to know if it's inherited from the core VCL base class, whatever it may be, or if it's the base class from FMX FireMonkey, or if it's from the very root class of MFC. You don't need to care about that. What you're just doing is like adapting your class to be able to call those functions that you need. In this case, just let me show it again, is this ones. You just want your class. You just want your algorithm class, which is the linear regression class, be able to update itself, to feedback itself to the main application to say, hey, look, do this update on your screen without knowing at all how it will be done. And that was the key thing of showing you the two samples, the console app versus the GUI app. The linear regression class is exactly the same. It doesn't care. It doesn't know actually if it's being called from a GUI app or from a console app. It is actually your app class. Again, sounds redundant, but your app class, which in case of a GUI application like here, has to be created anyhow. Your framework will create this class as you design your application. Then you just need to add those methods to your class that is already being created by. So here, the combination of doing this and then when calling the run method, what you're saying is creating your linear regression method, and when creating it, telling them, hey, look, the specific class of my application at this moment is this one, is the GUI one. If you are in the console one, when you're calling the run method, you are telling him, look, this is the specific class that I have right now. And the only intention is that when the compiler, C++ compiler compiles your code, it will only look that actually, yes, this class does implement those functions that you need for the linear class. That's it. Then going back to your question, this is not polymorphism. This is a neat and clever use of templates. This is more like adapter pattern. We are adapting two classes by interfacing them with a generic pattern. The linear class actually doesn't know at all what's the underlying class for your application. It only knows that it can call these functions. And when it calls these functions, then it's your own job now in the GUI and the application domain to do the actual work for doing the updates. So to answer that question, this is not polymorphism at all. It's actually like adapting. This would be called in theory is an adapter method when you adapt two classes. And since they are resolved at compile time, there is no impact at all. The only impact, as I already explained here with the GUI app, the only impact is on those progress that might be slower on the GUI version compared to the console version. So you need to do some clever workaround on your side to avoid the performance impact, like the one I did here by adding this flag, update only every 10 iterations instead of immediately. On the console app, there was a no-brainer because console apps are much faster to update on the screen. But yeah, that's the only, I would say, catch, or the thing you need to do is measure on which areas you have an impact. But the added value of having the progress shown to the end user, it totally supersedes any performance impact if you do your due diligence. As I have explained, is maybe an impact of 10%, maybe 20% on the final speed will not be noticeable for the end user as long as he gets this feedback. He will be happy because he has some progress. He's happy on seeing what's going on. But if what you do, it takes double or triple time, then yeah, they will complain.
Awesome. Yeah, thank you for that comprehensive answer. We really don't have many more questions. So that's a good thing because we're actually coming up on our time here. So just wanted to say thank you again, Miguel, for this very informative presentation, for the preparation that you put into it. And then thank you as well to all of our attendees for being here and giving us some of your time. Hope that you got something out of today's presentation, and make sure that you join us again tomorrow, where we will look at maps, C++ maps with our own David Millington. Thank you, everyone. And again, thank you, Miguel.
Thank you, everyone. Bye.
Bye.